This is the second part of the light's dual nature presentation. You can see the learning targets that we hit up in our last video using the equation C equals lambda nu to calculate wavelength and frequency. And then we also looked at ordering waves in electromagnetic spectrum by their wavelength, frequency, and energy. In this video, we'll be explaining the photoelectric effect and how Einstein used what we now call the dual nature of light to explain it. So first, a little bit of background on something called the quantum concept. Back in the late 19th century, there was a problem in physics known as the Blackbody Problem. Now, as far as what that is, it's not really of our concern. It dealt with the energy emitted by objects as they were heated and the observations that were being made. What is important to us, though, is a little snippet of the solution to this that will become important to us. This solution was proposed by a physicist by the name of Max Planck back in the year 1900. And here is a picture of Max Planck. And his solution was this. He proposed that the energy of any vibrating system in other words, atoms, these atoms are always moving around, they always have a little bit of vibration, that energy is quantized. And what that simply means is that the energy is only emitted in discrete amounts or certain amounts. If something is discrete, that means it can't be, in this case, energy can't be emitted in any random amount. There's some minimum amount that can be emitted. And he determined an equation for this. He determined that the amount of this energy is equal to some constant, which we'll give that here in a second, times the frequency of the vibration. So turning that into an equation, which we simply call Planck's law, the constant being a number 6.626 times 10 to the negative 34th joule seconds. Take note of that unit there. It's not joules. The capital letter J is the unit joule. It's a unit for energy, but it's joules times seconds, and that is known as Planck's constant, which has the symbol lowercase letter h. So if we just plug this into this equation that we used earlier, we have the energy of a quantum. We'll explain what that quantum is here in just a second. The energy of a quantum is equal to h, which is Planck's constant, times nu, which from the previous video we know that is frequency. So the energy of a quantum equals Planck's constant times the frequency of the vibration. And the quantum is simply the minimum amount of energy that can be absorbed or emitted by atoms. And this solution here was in fact a solution to what was known as the Blackbody problem. Again, we're not really concerned about what that actually was. If you wanted to know more about that, you could certainly look that up and find all sorts of information about what the Blackbody problem was. But what is important to us is this equation and how it will affect something else we're going to learn about here in a second. This is a link to a video. It's not real great. I've used it in the past. I'm not going to show it to you guys here. But if you wanted to click on this link in the PowerPoint, you certainly could. It's a pretty short video, 3-4 minutes. It's animated and it's kind of hard to understand because the talking goes so fast. But there are a couple good things in there if you want to check it out. All right. So this brings us to what we know as the photoelectric effect. This is what you guys did the simulation on for your homework last night or at some point earlier. And simply what it is, it's the phenomenon where electrons are ejected from a metal surface when light of some minimum frequency strikes its surface. You saw in the simulation that if the frequency wasn't high enough, then the electrons were not ejected from the metal. So there is some minimum frequency there. And this is a link to that simulation, which you guys have already gone through. But if you want to click on that again at some point, there's the link. And the thing about this photoelectric effect is the observations that you all made in that simulation, those did not match classical physics. In other words, they didn't match what we would expect would occur if light were in fact a wave, as we have learned about so far. So the phenomenon or the observations that didn't match. First of all, the fact that there was some minimum frequency that had to be met. Based on our understanding of what light was at the time when we first observed this, that shouldn't have been the case. Any frequency should have worked, at least eventually. You saw that whenever you increase the frequency past that minimum frequency, that the electrons were ejected faster. Again, the model in classical physics could not explain that. And then finally, increasing the intensity of the light gave you more electrons that were ejected. And again, classical physics did not predict that. In fact, classical physics would have reversed these two predictions, these last two, that increasing the frequency would have given us more electrons and increasing the intensity would have ejected faster electrons. So we had to have a way of explaining this. Well, the explanation and the proposed solution came from Albert Einstein, the Einstein that you are all familiar with, or at least heard of before, in 1905. And this is actually what Einstein ended up winning a Nobel Prize for, his only Nobel Prize. Here's a picture of a younger Albert Einstein. And his solution that he ended up winning the Nobel Prize for was the fact that light has a dual nature. In other words, it can act as both a wave, as we have been learning about the last couple of days, but also it can be thought of as a particle, kind of like an electron. And this particle is simply a beam of massless energy particles that Einstein called quanta. Now, the reason he called them quanta goes directly back to what we just talked about with Planck's work and that term quantum. He looked at it as a minimum amount of energy. Now these particles are called photons. These particles of light are called photons. So that's the term that we'll use. But Einstein did, in fact, call them quanta. So thinking of light as a stream of particles instead of a wave does explain the photoelectric effect phenomenon. And we'll go through each of these explanations here. First of all, the observation that there was in fact a minimum frequency that had to be reached, because if the light had too low of a frequency, we did not get any electrons that were emitted. The reason why this happens, according to Einstein, was that when the frequency is too low, that means those individual particles, again we call those particles photons, that they did not have enough energy to rip off or remove an electron from an atom. There just wasn't enough energy there to get that electron pulled away from the atom. So we didn't see any electrons get ejected. The second observation, the fact that if we increase the frequency past the minimum, and that gave us faster electrons, Einstein simply explained it this way, that if you go past the minimum frequency, those individual photons, again the photons, the particles of light, the extra energy they have goes to the electrons. So the electrons simply get ejected faster. The more energy the photons have, the more energy the electrons will have that are ejected, and that will make them go faster. And then finally, the last observation, the higher intensity observation, which we saw it gave us more electrons, was simply this. If you have a greater intensity light, that simply means there's more light. In other words, there's more photons. Now, the total amount of energy is more because there's more light, but however, the individual photons still have the same amount of energy. So even though there are more photons, the photons don't have any more energy than they did before. So those additional photons simply will eject more electrons. The electrons don't go any faster because the photons don't have any more energy, but we just get more electrons because there are more photons. So what this leads to is a modification of Planck's equation. In Planck's equation, this referred to the energy of a quantum. Recall that quantum was the minimum amount of energy that atoms could emit or absorb, and that was equal to Planck's constant times the frequency of the vibration. Well, after Einstein comes along and talks about these particles of light, this equation gets modified a little bit, where now instead of calling it the energy of a photon, the energy of a quantum, we call it the energy of a photon. In other words, that this characteristic is actually a characteristic of light itself, that this minimum amount of energy comes about because the energy that's being absorbed and emitted only comes in packets of energy that make up the photon. So the equation itself is really the same. It's still energy equals the Planck's constant times frequency. It's just that we look at what that energy comes from or why it arises. It's just a little different. Alright, so that ends this video. We've explained the photoelectric effect and how Einstein used the dual nature of light to explain it. The next video is going to be a pretty short one. We'll hit up this equation of E equals h nu. We'll do a couple, 2 or 3 example calculations in the next video so you guys can see how that works.